everyone. I'm very pleased today to welcome to our control seminar Professor Vamudakis, Kyriakos Vamudakis from Georgia Tech, the Aerospace Engineering Department. So I've known Kyriakos for a number of years now through the controls community, and his career path has been rich with starting his studies in the US at the University of Texas Arlington and moving to research appointments and careers at important universities like Virginia Tech, Santa Barbara, and now Georgia Tech for a couple of years now. His work has been recognized by a number of awards, including a Young Investigator Award, another DoD Young Investigator Award, and NSF Career Award, including a number of nominations and other distinctions. Kyriakos is also very active in the service to our community. He's associate editor and guest editor in most of the journals and controls conferences.
I'm serving too much.
Yes, so if you receive a review request, please accept it.
Good, thank you.
And with that, today he will be talking about bridging models and data, enhancing cyber-physical system security and control. So with that, please join me in welcoming him.
Thank you very much. Thank you very much, everybody, for being here. Thank you very much, Dimitra, for the nice words. And it's a pleasure being here. It's my first time in Ann Arbor. It's good to see friends and then make new ones. So again, this is the first time I give this talk, so I'll be happy to get comments on that. It's our most recent work that I did with one of my PhD students. So let's see. So my lab is called Intelligent Cyber-Physical Systems. So of course, in a control seminar, I don't have to give a background, but I'll give a brief one. So again, it combines cyber and physical components. Cyber components that has computation and communication, while physical components, they're actuators and sensors. Of course, they're everywhere. I mean, from military, healthcare, infrastructure, transportation. So in our group, we work in the intersection of security and control. And what I mean by that is we want to design resilient controllers such that we can guarantee that the sensor and actuators, they provide us what we want, and eventually control our system in an optimal or close to optimal way. Okay, and so people, they have tried model-based designs, model-free designs. Of course, in a model-based design, you can verify easier things, okay? You can identify and verify different vulnerabilities. You can see some controllers, and it's easy to do rapid prototyping. So what we will do here is we will take two very important things in control, which is controllability, observability, and we will see how an attacker can drive you outside your controllability or observability, and what is the distance, okay? So what is the distance that you are, I will say, secure, and you will see some things on that one. And then eventually, we will combine model-based and model-free controllers in an elegant way that you will see pretty soon. Okay, so let's go to controllers 101. So let's say we have a linear system, okay, the classical one, x.ax plus pu, and then everything that is self-explanatory. And I will consider, as I said, two core system properties, and I will check what an attacker can do to drive us far from observability and controllability. And we will define something that we will call distance to uncontrollability and distance to unobservability. Okay, so this is what I just said. So here you see two components. So the red ones are actually the attack vectors, and this is how the attack will influence the system, such that with this influence, it can change how we see controllability or observability. Of course, if I don't have AX and AY, of course, in order for me to control the system, I have to assume A is controllable. And of course, if I go to observability, I have to assume that AC is observable. And for now, that we will say that we will assume that we're controllable without the attacks and observable without the attacks. Okay, so this is what I said, okay? So I will quantify this distance to uncontrollability and observability, and I will find what is the best attack that can take us outside our controllability or observability. And then, of course, this will eventually inform the operator or the defender or the designer to select appropriate actuators and sensors, and then eventually improve resilience. Okay, so we will start with observability first. Okay, so let's say I have this leaky side channel, okay, that exposes information, K, as you see here, to a potential bad actor. Okay, so of course, I will assume that the attacker can observe the signal, which we'll call it KT now, and KT is KX, where K is, you will see, is the attack information channel. Again, don't confuse K with the Kalman gain. It's not a controller here. Okay, so K is the attack information channel. Okay, of course, you can see that if I take K to be the identity, then I have access to the full state. If I have K equals to C, then I can measure past of the states. Okay, again, classical things, not too interesting up to now. Okay, so let's get to the interesting things. So why is this very important? And we think that in my lab that it was worth exploring. Because the attacker can actually scale this K that actually can check and adversely design this AX and AY that you saw in the previous slides. Okay, so AX is the one that you change your state, and AY is the one that you change your output. Of course, both of them, they're interdependent. Okay, so for now, we will assume that AX and AY, they have this form, okay, where gamma A and gamma C, their gains, and eventually the attacker has to find the best gamma A and gamma C such that it can drive us to unobservability here. Okay, so again, let's go back to our little 101 controls. Of course, if I substitute these two things into my state space, then you get this one over here. Okay, and so again, the attacker has to design this gamma A and gamma C such that this pair is unobservable. Okay, so let's see how easy it will be for an attacker to make the system unobservable. So there is this notion which is called distance to unobservability. Okay, so again, we have to solve this problem by finding gamma A and gamma C, okay, the best gamma A and gamma C. Again, this is the least effort attack that can take us out of the observability, okay? And again, you will see that we can quantify this distance, okay? So again, so here we consider a complex gamma A, gamma C, okay? And eventually I can find this omega, which is the set that I am observable, and then outside of it, I'm unobservable, okay? Okay, so let's now, again, you will see that's actually a pretty simple problem. So let's say again, remember AEC is observable, okay? And I want to find my gamma A and gamma C such that this pair is unobservable, okay? So what eventually I have to do is I have to find this S, which is a number, constant, sorry, and V, which is a vector, such that these two things hold. Again, this is classical PBH tests, okay? Okay, so let's see how we can do that efficiently, okay? So of course, if this exists, okay, then I can write down the gamma A and gamma C, okay? Again, everything I think here is self-explanatory. So the V's and the S are the ones that I have to find, okay? Such that the gamma A and the gamma C, they're the best attack that can actually make my system unobservable. Okay, again, that's what I said. Now, let's actually start formulating the optimization problem. Remember that I have to find this omega, and I want to minimize this, okay, given with respect to S and V. Okay, I told you the only unknowns here is S and V, okay? Of course, the problem is a little complicated there. It doesn't look that complicated, but it's a little complicated. So eventually, I can reduce it to this problem, okay, which is only with respect to V, okay? Again, this is just a minimization problem, and I can find this set over here. So you will see that the bounds on the distance measure, if we solve this problem, they don't depend on A, okay? So everything depends on C and K, okay? And remember, K is how you scale your state such that you can get A, X, and Y into your into the attack framework. Okay. So let's take the cases separately. So remember, I had two cases. One that I had full state access, okay, and then one that I had like partial state access. So let's say first I have full state access, okay? So again, remember that the K was identity matrix. So eventually I want to solve this problem, okay? Which is again a reformulation of what you saw before. This is for the case of that I have full state access. So if now the K that you see over there is column orthonormal, okay, then K is equivalent to the case of full state feedback, okay? Again, remember that the effect on omega, this is the distance to unobservability, okay? So I can find all the distances, and then the effect on omega, if I can observe the whole state with a column, is equivalent, I will say, to the case of full state access, okay? So again, I want you to see that column orthonormality of K is equivalent to the case of full state access. Okay, so now the case where you have partial information of the state, which is your sensors. So same thing here, okay? So modifying A and C will not improve the distance to uncontrollability, unobservability, sorry, okay? So this means that if my K is equal to C, even if I change my A, okay, there's no improvement, okay? So this was actually an interesting finding. Okay, so of course, we modified it a little there for the distance measure to be easier to solve. So eventually we have something like that where epsilon is studied for relaxation here, okay? Yes.
So I just did like observability and I do output feedback. Observability is unchanged by doing output feedback. So that's a version of what you're saying is if the attacker only has output feedback, they can't do anything.
Yes. Again, if we have orthogonality constraints, this is not trivial to solve analytically. So what we do, we use descent-based numerical procedures to solve this problem that you see over there. Okay, so now this is a pseudocode. Again, this is the optimization that we will solve. And here you see a pseudocode that you compute the distance measure omega. And I want you to pay attention to these three lines, okay? So the third line, I say, generate this psi, which actually we generated based on using the gradient of G, okay? Again, remember, I use a gradient descent approach here. And then for the blue one, we do some K transformations, and then eventually have the decision variable, okay? But it's just a simple, it looks complicated, but it's a very simple way to solve this optimization that you see over here. But I want you to focus on this one. We have a solution for that one, but this is the main idea here. So let's actually see how things can influence each other in a system. So we consider different systems. So let's say I have this A matrix. I have this K, which is, you remember, it's a scale. It's identity, so I have a full state information. And I have two Cs, okay? C1 and C2. What we do here is I want to vary my phi, okay, in C1 and C2, and I want to compute the two omegas, okay? Again, you have the system, okay, and you want to change phi's, and then you find the omegas from the distance that you saw before, okay? From theory, I have closed form solutions, right? I can compute them. So let's see what happens. So what you see here, this is for omega C1 and K, okay? So you see that the bound was computed to be 0, 1/2, okay? So everything inside here is good to go, okay? And then same for the C2 part, okay? Again, everything inside here is good to go. So now let's consider a different framework, okay? So let's see what happens when I change my A matrix, okay? So I have my A1 and A2, and then I change my theta, okay? So again, I change my theta here. You see theta appears here and here. Everything else is constant, okay? So again, we compute the distances for the first system and for the second system, okay? And both of them actually, because remember, the A doesn't influence that, right? So, and it's between these two numbers, okay? So again, changing A, you see, doesn't change my bounds, okay? Of course, I have the influence that you see in omega with the blue and for A1 and A2, okay? Again, these are the two distance measures, and this is the effect of matrix A, okay? Another one is, so what happens when I have different instances of the K? Remember, the K was the scaling one, okay? So I have this F-16 fighter jet.
I have one of them.
So, and then we have this A matrix, this C matrix, okay? Again, we have two sensor outputs, and then I have different instances of K, okay? So let's see what happens. So what you see here is, again, you see that the Kj changes, okay? So here you see different Ks, okay? This is the identity and then other different Ks. And you see that this is quantifiable. And also I want you to observe that for K4 and K5, because they're column orthonormal, then I have the same result. That's why you see this one over here, okay? And again, all these things, they follow our closed form theoretical guarantees. Yes?
I'm curious, like, so I can understand how you'd affect the output of a system like an F-16, but how do you affect the dynamics, like the X star? Like, how do you affect the AX?
I mean, you can consider actuator attacks where you go inside the actuator and you change stuff inside. So here you consider actuator attacks and sensor attacks, and then you see how your distance to unobservability is changed by changing different things.
And then you're like limited to to what the actuators can do, I guess, on the input space, right?
Yeah. You can consider some constraints there as well. Okay, so of course, when your K is equal to C, then you can see different things as well. I don't want to bore you with this one anymore, but we have done generate like random observable pairs. Okay, we set K equals to C, and then we get different things. And of course, we want to do that because we want to validate the result that if we have K equals to C, then our distance is 1. Okay, so now let's go to another one. Again, you will think that they're somehow dual. Let's see what happens. So now we have only actuator attacks because again, appears on this way, okay, the alpha. Before we had both and we want to see how you can influence output. So here the attack vector and the attack channel are given by DNA, okay? So again, this is how the attacker can do this attack by scaling your X and scaling your U, okay? Again, I assume that the beginning of my I and B is controllable, and eventually I want to find the lambda alpha, lambda B to make this uncontrollable. Okay, so again, similar with before. So as I said, I want to find lambda alpha, lambda B. So I have to solve, I have to find this, which is the distance to uncontrollability. And again, we solve similar problems with before. I can relax it, okay? And And eventually, I can solve whatever you saw before, but with some minor adjustments. So now you saw that in order for me to solve this, I have A and B. Before, I didn't have information about dynamics. So what we want to do here is, instead of knowing the dynamics, as you see here, we wanted to plug and play. So we want to identify the dynamics in real time. So we want to learn A, B, and D. Okay. Again, this is another way to do things. Okay, so we will call our friends that they do parameter identification, and then it's like, okay, how we can do that? So instead of having A, B, and D, I want to approximate A, B, and D, and then I will feed them back to my distance to uncontrollability. Okay, and then my distance to uncontrollability will be dependent on these identifiers. Again, I can estimate this A, B, and D by using, for example, some neural nets with Wish's approximations, where I can use an infinite amount of basis and I can approximate any function, right? But again, this is easier because A, B, and D there, let's say for these scenarios, they're time invariant, okay? Again, this is how you design the estimation model, okay? And these are the tuning laws, classical gradient descent. And eventually, we have guarantees that my estimated ones are exactly the ones that you have before. Okay, so let's see how this can work. So we have this A, B, and D, okay? And then I want to vary my psi that you see in A. And I want to vary my psi given these 6 cases, okay? And of course, I don't know exactly A, B, and D. And of course, I also have this sensor in here. So what I want to do is I want to first identify A, B, and D, and then compute my distance to uncontrollability. Again, my theoretical bounds for all the xi's that we had here, they're given by these 2 numbers, okay? Again, everything what we have here is verifiable, and the theoretical bounds from the theorems before, they give you these numbers. And of course, as you will see here, I don't have a case, but what we do here is I do parameter identification of A, B, and D. And then eventually, so here you see that my theta A, my theta B, and my theta D, they converge to A, B, and D, okay? As I get more samples, and this is for all size, okay? And then here are my bounds, okay? And actually remember that I didn't have any information about the system, and still I obey the bounds if I knew the system, okay? So yeah, so these are the distance measures for the uncontrollability. Okay, so right on time, perfect. So here, what we did is we derive adversarial distances to unobservability and controllability, and then we find explicit bounds on the distance measures, and then we show different examples. So now we will take it a little bit further. So I know there's a lot of things about model-free, model-based reinforcement learning. So what we eventually did was we want to combine model-based with model-free techniques, okay? So let's see what I mean by that. So yeah, so we already know all these things. So what we will do is that we don't always know the model, but sometimes we have information about the model. So what we want is to incorporate this information to the model if we know it. And of course, we want to do everything in an optimal way. And that's why we have that. So let's see what happens. So we have 2 different techniques. We have the model-based ones, okay? Which of course, somebody will say, okay, if I have the model, right, I can solve my, let's say in a linear case, as you will see, but we will do it in a linear case. But let's say the linear case, if I know the model, then I can solve the Riccati offline in my computer, okay? And then if my model doesn't change, this will be good to go, right? So I have to synthesize offline. Of course, it's that efficient because I compute only 1 Riccati. I don't have to do any computations in real time. But of course, the model sometimes changes, right? So if you have an aircraft and if you burn fuel, your mass changes. So whatever you computed before, it's not optimal, okay? Because you have changed your mass. Although the model-free methods, right? So if I don't depend on the model, I'll somehow be more accurate because my algorithm will not depend on anything that has to do with physics. And of course, I can do everything in real time. But I have a problem because this is data intensive. What I mean is like, as I get data from my trajectories, I have to do computations in real time. And it's not always easy. So what we eventually want to do is combine these two things, okay? And avoid the suboptimality and the data intensivity, if these words exist in English. Okay, so let's see how this can work when you combine model-based and model-free techniques for the optimal regulation problem. Okay? So again, we will consider different cases, okay? So we can switch between model-based and model-free controllers, okay? We can use them concurrently, okay? Or we will use model-based controllers at always an initial condition for the model-free algorithm, okay? But all these things, they're considered in our framework. So for now, let's consider these two cases. Again, remember that one of the problems was that data collection is very expensive, okay? So if we can avoid data collection because I don't know the model exactly, okay? For me to tolerate some suboptimality, so then I can converge faster, but probably there will be a trade-off between accuracy and data efficiency. Okay, now let's go back to our little models. Again, I consider I have a controllable system. Again, we have done it for linear and nonlinear cases. We will show a linear case here. So let's say I have a controllable system, A and B. This is my actual system. And I have an available nominal model, okay? As I said, AB here is considered unknown, while my nominal model is considered known, okay? So let's see what happens. Again, I don't know how close this can be because I don't know A and B, right? If I knew A and B, I would have solved the problem. So again, we can work on minimizing this cost function, where it's a classical, let's say, LQR case, where I want to penalize my states, I want to penalize my control, okay? And I want to find this UP that I will tell you pretty soon what it is. But I want you to remember here, okay? So I have my actual controller, my actual systems that I want to control, and I have an available nominal model, okay? And I will consider that I have a controller, okay, that has been synthesized offline using the model to minimize J, okay? So, again, remember that whatever I have, if the model, okay, let's go back again to the slide. So here, this one, I can compute a U for this model because I know AM and BM. I can solve it, right? I can call our friends. Math works, and they can tell me, okay, you can use ICARE, and then you can find your P and K, okay? And then you can find this UN, okay? Again, this I put U here because I want to generalize it from my actual model. But what I have here is I have this UN, okay? So, again, if the model is inaccurate, of course, will be suboptimal, right? It won't be the U that I actually want to build in the system. Okay, so let's see how this is going to work. So we can have switching, right? So as you can expect, I want to switch between model-free and model-based techniques, right? So the first part is the model-based one. So the one is if I knew the model, right? So I can substitute my U with the okay? And of course, this is when I have information about my model, right? And or if I don't know and I want to use my model-free technique, I use the plus a correction term, okay? But the correction term will come from my from a model-free control technique, okay? And so this one is what we call a composite controller, okay, which is and U tilted. And the TS is when I will switch between the model-based and the model-free techniques. Okay, so again, this is just a schematic, right? And then whenever this sampling happens, then I use both things, okay? Because you can see it here, and then model-free. Okay, so what we want to find is when to switch between the model-based, model-free, okay? And I'm going to do that because I want to find this utility also using only trajectory data. Remember, this is the model-free component, right? So I have information about the system, which is given my model-based one. But of course, I don't know how inexact it is. And eventually, I want to use my composite controller, okay? But this composite controller will be adjusted by the model-free component, which is the utility, okay? And I want to do that in a real-time scenario without information about A and B, right? Remember, I only know AM and BM, okay? Which can be very inaccurate. Okay, so now let's go back to the classical problem. So what eventually I want to do, I want to minimize this J that you saw before, right? And subject to these constraints, okay? If I knew the model, right, it will be straightforward to solve, okay? And minus R inverse B transpose P, and the P is the solution to the Riccati equation. Again, you see that here I have information about the dynamics. This is a model-based part, okay? So A and B unknown, UP cannot be computed here. So let's see how we can do it. Let's see where we are. Yeah, so this is the model-based controller, right? So AM and BM, okay? Again, here I know AB and BM, so I can compute these two things. But of course, as you know, AM, BM is available, so the UM is no. So we want to see what happens when we don't know it. Okay, so let's see how we can find the switching moment where you switch between your model-based and your model-free. The trajectory of the system under this UM is this X can be generated by this X dot here. Okay. Of course, this will give me one trajectory, which will be XM, right? And I will have eventually a model mismatch, right? Again, this is classical techniques. So I have the trajectory of the system under UM, okay? And then I have the known model that I know. So I want to check how close these two are, right? So if I knew the model, which is this one, right? And then if I don't know the model, is this one. So let's say if I put the same controller in both of them, I get two different trajectories, and then I check this difference here, okay? So let's see though how we can compute it and how suboptimal we will be, okay? Again, this is the optimal one, and this is because, again, this is the model-based one. So this will give me an error, okay? Remember the error is XT minus XM, okay? And of course, this Xi is a constant that is how much I can tolerate suboptimality. But of course, this one cannot be checked, right? So we have to find a better way to do that. So let's see how we can do that. So let's see, again, so what we will do here is I will take the Hamilton-Jacobi equation, and then I will check how far it will be from the actual one, okay? You know that if I had the Hamilton-Jacobi-Bellman equation, it's equal to 0, right? But if I have the optimal controller there. But if I have any other controller there, it's not equal to 0, okay? So we want to explore what happens if I take the difference between the star, which is 0, which is invisible here, right? Because I have a 0 here, which is the Hamilton-Jacobi-Bellman equation, or the Riccati equation, again, in the linear case, which is this one. So if I take the difference, then eventually you will see that I get something that I can check, right? So here you see that I have the maximum eigenvalue of R, I have the Xi, and I have the difference between the two state trajectories, okay? So let's see if we can do better than that. If, let's say, I have UM has a degree of suboptimality Xi, I can use Lyapunov analysis, I will say, and I can provide that the difference between X and XM is upper bounded by these quantities over here, okay? Which again, I know everything here, right? I know the state and I know because I have computed it, okay? And everything else is just not quantity in the LQR, okay? So under bar means minimum, upper bar means maximum, okay? And xi is how I can tolerate my suboptimality. Okay, so now that I have this one, I can find my switching instant, okay? So for those of you who are actually familiar with event trigger control, this is actually pretty similar to that, right? So instead of operating under open and closed loop, here you operate under model-based and model-free techniques, okay? So for those of you who are familiar with event triggered, you will see that if you do optimal event triggered, then you will see you get something that looks like that, okay? So in other words, when you switch between, when you trigger that you need the measurement from your X and you close the loop, I don't know if you're not familiar with event trigger. So event trigger is, I close the loop every time an event happens, okay? And then an event happens in the optimal event trigger case when I'm deviating from optimality or I'm about to be unstable, okay? So then an event is triggered and I close the loop, okay? And then I continue. This is something like that, okay? But instead of doing open and closed loop, we just do model-free and model-based, okay? So now we have designed the UM, right? And then we want to design now the composite controller, okay? So again, for your UM, I have already a closed form solution, and then I have this U tilted. So now I have this new system here, okay? Where A tilted is A minus BR inverse B transpose PM, okay? Where I don't know A, I don't know B, I know BM and I know PM, okay? And of course, I don't know B over here as well. Okay, so let's see how we can compute now this composite controller that will let us switch to the model-free technique. So now, instead of solving the problem that you saw before with the UM, I solved this problem with the U tilted, okay? So again, this is just this one here, okay? Where I'm solving this problem, okay? So eventually, if I knew the system, okay, it's given by this. But of course, I don't know anything about the B or all these things, okay? Again, if I knew the system, I wouldn't have to do all these things. I would have go to the previous one. But this actually will give us a direction of what I have to learn here, okay? So what we will do, we will use a model-free method to compute this U star, okay? So again, if we go to the learning world, okay, so you can do different techniques. You can use Polish iteration, or you can use value iteration. What we pick to do here is something. Okay, so let me first talk about that one. So policy evaluation, it checks how good your policy is, okay? And policy improvement, it updates your policy, okay? So what you see here is I'm solving this Lyapunov equation for mu I, okay? For Vi, sorry, and then I update my mu I, okay? Again, this is iterative. Then this actually has been shown to converge by different people, including Gary Hewer, that he actually showed that this converges after some iterations, okay? But again, here you see that there is the model, so we have to find better ways to do that. Okay, I said it already. So there are ways that we have developed in our group, which is called integral reinforcement learning. And we will do it in an off policy. Again, enough policy learning means that I have a behavior policy and then I have a policy that I want to create data, okay? So with one policy I create data and with the other one I update my controller, okay? So the first part though that I have to approximate is I have to approximate how good my controller is, okay? So this is called critic, okay? We'll criticize, let's say, how good my controller is. And then the actor is actually an approximation of my policy, okay? Or my control input, as you can say that. So if I find ways to tune this WI-V and WI-U, then I can convert my VI hat and mu I hat, they can convert to the optimal solution. Okay. So, and again, I want to do that with the least information about the system. Okay, so as I told you, we have a policy that we apply to the system to create some data. And then after that, we use some least squares to solve it for the weights. Okay. Again, all these things is completely model free. Okay, let's see how this can work in a simulation. Again, we go to F16s, and we have 3 states and 2 inputs. So we have a joke with Vasilis about if F16s uses PIDs. So, okay, so we have this F16 fighter jet with 3 states and 2 inputs, and I have an initial condition 9 minus x15. And again, this is the parameters, and this is my xi, which is how I can tolerate and how much suboptimality I have to spend. So, so let's see what happens when the first case that I have an inaccurate model. So let's say the first one where my AM, which is the model based one, is 0.25A, okay? So this is an inaccurate model for A, and then BM and B, they're the same. Okay? So you see the states, and you see the gray is when you switch between your model-based and your model-free techniques, okay? Then you see it's pretty fast, okay? So here, because I have a model mismatch, the controller understands this, and then I switch to my model-free one. Okay, and then of course, even in this case, eventually I convert to the optimal solution. Let's say if I have an exact model, right? A fairly accurate model, you will see that I will barely even switch, okay? So you see that AM is 0.9A, okay? And the BM equals to B. So I don't switch, okay? Because it's good enough for me, because I have sacrificed some suboptimality, okay? And then, so what we did here, we saw how model-free and model-based things can be interact. I found a way that I can guarantee that with the switching time, I can guarantee that from a model-based controller, I can switch to a composite controller. And yeah, and then with that, I think I'm right on time. So thank you very much, and I'll be happy to answer any questions.
So we have time for questions? Yes.
My question's on the first part, which is you've got this distance to unobservability or distance to
Uncontrollability?
controllability. And it's based on the PVH test. And so I'm wondering, like, have you thought about using Gramians as like the metric? Because usually the PVH test, it's a rank test. And so you mentioned even in your algorithms, there's discontinuity issues.
Yes, yes, yes.
So like the condition number of pushing the condition number of controllability or observability Gramians. Would there be a way of formulating it that way?
Probably it will be. I don't know if it will give me how far I am.
Yeah.
It will give me maybe that I'm controllable or observable, but it will not probably tell me how far I am or how close I am. But yeah, as you said, there are numerical issues, so we had to assume that it was complex, not real. And then, yeah, but maybe there are ways to define the distance with the controllability Gramian, but yeah, I'm not familiar with it.
Maybe one more quick follow-up.
Sure.
Since you're solving for complex games, you get the distances.
Mm-hmm.
Can you actually back out what the attacker would be doing in terms of like real? You had feedback matrices that they were using, but those would have to be real for them to implement that.
Yes, 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 yes. So your gammas are will be real,
Yeah.
okay? And we always want to find the best gammas that can take you outside. So reconstruct the actual one. Yeah, we haven't worked on that, but it will be interesting. So here we want to find the best one that they can do with the least damage to us. Yes.
And the second part of your talk, where you're doing the switching between model-based and model-free, so you switch only once.
Yeah,
Would
yeah.
it make sense to, would it be cases where you might want to keep switching in between? Would it be applicable, let's say, if you had a nonlinear case maybe, or?
So
other-
if your system switches, changes again, so I think you will see another switch. But for here, we always consider only one switch. But yeah, that's, you can switch many times as long as there's some conditions are true. Because remember, you cannot switch fast enough because you will never be able to get anything. But you can switch as long as there's a time that is greater than the time that you can find for Zeno behavior.
Yeah, or avoiding the two behavior, but in your model-free approach, I guess you have some guarantees of convergence. That's why probably you don't need to switch again, right?
Yes. But in a case where, again, you have a person, okay, oh, I think that the system is closer to this one, then it will change again. Yeah.
And the fact that you can optimize separately for your U tilde and your time of switching, is it an inherent separation principle, I suppose? Or like if you had a nonlinear model, could what?
Oh, if you had a nonlinear model,
Yeah, if you, what if whether it would have an interesting problem of optimizing for the U tilde that affects the T switch. Whether that would be an interesting, whether you have thought about.
I haven't thought about that, but it's interesting.
Yeah.
So you co-design your U and your time.
Yeah,
Interesting.
it sounds like because you're in the linear regime, like you
Yeah.
optimize them separately, it's.
And also probably we can also do some fixed time things or prescribed time where your switching time has to be below your fixed time upper bound or something like that. I know you have been working on fixed time and prescribed time, so maybe something like that there too.
Other questions? Yeah.
Yeah, going back to unobservability and uncontrollability part. This may be a very naive question, but you defined some bounds and then you showed some like evolution with phi, right? And most of them were like bounds were tight, but in one of them, it was like the plot was loose, like especially in the sine and cosine one. Was there a reason, or is just like luck?
Let me see.
In the unobservability part.
Okay. Are you talking about
Yeah.
this one?
Yeah, for
Okay.
example, like in almost all of the plots, when you define the bound, it was almost tight, but not in the sine case. Sine and cosine case.
Oh, okay. I now I know. So you mean the red one because the other one is tied.
Yeah, the red one looks tighter than the
Yes.
blue. Yeah. It's a problem.
So it's because the bound on the second one was dependent on phi. So, and then the other one is constant and it was true for all phi's. So when we derived it for the second part, because of these cases here, so explicitly your phi gets over there. Yeah, so that's what you mean, right?
Yeah, but
So the one is constant for all phi's, for the first one, for C1, but for the C2, then you depend on phi.
I would still expect, again, like this may be very naive, like I would still expect the maximum value of the sinusoidal would reach, because it's sinusoidal, the upper
Yes,
bound of it.
yes. So you mean that your bound will change?
Or like, no, maybe bound can stay the same, but like in the maximum part, you would reach to that bound, like in the omega plot. So there's
This
a
one?
difference between like probably 1.5 to 1.4, like the
You mean
difference.
here?
Yeah.
Oh, because we didn't, maybe if you change your phi more, you will
Mhm.
probably see a tighter one. Yeah.
Maybe I have two questions.
Sure.
I think that's coming for the second part, but now that we're on the first part,
Sure.
I'm trying to understand. So essentially, okay, if you have this characterization,
Mm.
right, how do they help you to do defense? In the sense, how do they help you to? I suspect your defense is by changing your control input, there is no other thing, right? Your system is fixed.
Yes.
Because if I change the system, there's some new bound exist or whatsoever, but have you worked on that or any thoughts on that?
So here-
What happens with a U? How this helps to design the best U?
Actually, that's,
And I know you
That's-
changes the system, I know.
we're actually currently working on that. So given that we have these bounds, it's like how I can design my controller to even push and make my system back to inside the set. So it's a tough one because the attacks, I mean, if the attacks on it for the controllability, it's not difficult to do, but for the observability one, it's tough because you have two attack,
Yeah.
you can attack the state,
inputs.
yeah, two inputs, yeah. But yeah, this is eventually what we want to do is to design defense measures such that you can put a corrective input into the system, such that you can push it back inside the measure.
Yeah, it is interesting. Yeah, it's lovely. Yeah, I'm trying to connect with.
So we had,
Techniques, from Sino.
So here,
Like that and everything.
yeah, so here we want to take the attack side and see, okay, so how we can design such that we can get out of the omega.
Yeah. Okay, thank you.
Yeah.
And the second question is kind of
Mhm.
similar flavor, right?
Mhm.
So you have the model plate,
Mhm.
kind of essentially nominal control.
Yes,
And then
yeah.
something essentially you're hitting a threshold.
Yep.
And then you say, I do model free. How does this compare to, for all this before your threshold, or, I mean, from the beginning of time, you start collecting measurements, right?
Mhm.
Forget about persistent excitation or whatsoever. Yeah, just
Mhm.
collect measurements. So you
Mhm.
can start building models, right? Is it something equivalent? Essentially, is it some kind of a method of, simultaneous system identification and control where just you switch your, after a certain threshold, you switch your policy because you have learned already enough? Or it is, just at some point, just I'm switching and I'm just doing purely model free and I ignore all the previous data.
So,
Maybe I didn't follow completely, so maybe already I have lost the problem formulation here, but.
so let's say that I have an idea about my system. I have an idea about my system, okay? And let's say it's scaled. Let's say my A is scaled like 0.5, okay?
Yeah.
So if I use a completely model-free technique, I will need more data to
Yeah,
converge to the optimal solution.
yeah.
But if I use this model-based technique in the beginning, so I know, okay, I'm halfway there, okay?
Yeah.
So while I'm using some information that I know,
Yeah.
and then after that, I use this information to my advantage. And then after that, because, okay, so I collect this data, I use my AM, for example, but then, oh, okay, this is not good enough, so now I have to switch to the other one. So I already, whatever I have collected in the past, I use it to train my algorithm. Yeah.
Okay, so it's essentially, yeah.
That's why it's faster.
Maybe what I'm thinking, that
Yeah.
it is along the lines of how the
Yes, yeah.
problem is. Okay, yeah, thank you, yeah.
You're welcome. Yes.
I have like a very open-ended question. It goes back to like my friend defended his thesis recently, and it was about like attacks and defenses. So like one of the things that I learned there was you have your neural network, you attack it, and then people start developing defense mechanisms. And then attackers learn what is the defense mechanism about, and then they design an attack on that mechanism.
Cool.
So I'm thinking in the context of controllability here. Let's say you have a parametric system, as in the examples, and you decided to choose that, oh, there's a parameter that maximizes distance to uncontrollability, and that's my system. But to some extent, my assumption here is I know how is the attacker going to attack me.
Okay.
Do you think there's a way that based on these assumptions, a smarter attacker can actually like harm me more than the original attacker?
I mean, okay, so let's say that again, this is model-based techniques. The first ones are model-based. So I knew the information about the model. So let's say if you have an A and B, right? So there is only one controllability, distance to uncontrollability, right? If you see that I changed my phi just to see how this can be affected. But if I know the system and the attacker knows the system, right? A and B. So we both know that these are the bounds and the distance that kind of what you can do to take me out and makes me uncontrollable. Again, if you know the system. If you don't know the system, then you're right. So there's many entry points. And then, yeah, so that's why we try to do something in the controllability where we try to identify the system while we move. Of course, the attacker can make me identify something that is not correct as well. So yeah, so that's why we try eventually to design some other controllers that we can push us back into the correct omega. Yes.
Yeah, so a technical question, can we go back to the pseudocode for the second half of the talk?
Yes.
Where there's a least square procedure?
Yep.
So for computing the weights, the weight parameters.
Yeah. Here, right? Yeah.
Yes.
Yes.
So, I was wondering why least square here instead of gradient descent?
Oh, this is pure of policy. So you can use your favorite thing there because I have already collected data from before. So I use it to my advantage to compute the solution.
I see. So
Because remember that I switch after my composite, my model-based controller. So I have already have some data, and then I can use least squares to do it. So this will be, I will say, a little faster than gradient descent. But again, you can put your favorite thing there. It's the same thing. You can use recursive least squares, gradient descent, steepest descent, anything to compute this part.
this is for leveraging the data collected before.
Yeah.
Yes.
Yeah.
Thanks.
Let's check if there is any question on Zoom, or if some of the Zoom participants would like to ask a question, they should feel free to unmute and ask the question.
So you got it correctly.
Yeah, it captured me correctly now. Good. Okay, if there are no further questions, I think it's a good time to stop. Let me thank again.
Thank you very much.
Konuşmaya geldik sen.
Sonra 35'i de alacağız ha.
Works. Thank you very much.
You know,
Familia, Brin.